In the last video, we saw that continuous or at least uniformly continuous functions are always integrable on Jordan domains. So now what we are going to do is we are going to prove a proposition that lets us recognize or at least some domains as Jordan domains. So here's how we can write this. Let's let Y be a subset of our P minus 1. And let's let F and G be two functions whose domain is Y and whose range is the real numbers. And let's suppose I suppose we want to make Y be bounded because we want to say that F and G are integrable. On Y. And we only talk about integrability at this point. We can only integrate functions on bounded sets. We can only integrate bounded functions on bounded sets. So F and G are integrable. Then we're going to let X be a set in RP. X is the set of all ordered pairs YT. Y is in our domain Y, so Y is in our P minus 1 that has P coordinates. T is a real number that is between G of T and F of T. Sorry, G of Y and F of Y. And the conclusion is that X is a Jordan set. And in particular, I'm going to highlight a particularly useful case. If Y is a compact Jordan set, which since we're in RP just means closed and bounded, and F, G, and F and G are continuous, which we saw last time means they're integrable, then X is Jordan. And it's not too hard to prove that X is also closed and bounded, and so therefore it's also compact. So let's prove this. By our favorite proposition for showing that things are indeed integrable, there are rectangular covers P sub F and P sub G such that these are rectangular covers of Y such that the upper sum of F over our first cover minus the lower sum of F over our first cover. So because we're applying proposition 7.2.4, we have to start by picking a positive number epsilon. And exactly the same thing is true for G. And then by your first homework in this section, there is a cover P of Y that is a refinement of both PF and PG. So, and remember, taking a refinement just moves your upper and lower sums closer. So the upper sum of F over P minus the lower sum of F over P. Then let's go ahead and add the upper sum of G, the over P, and the lower sum of G over P. We're just adding our two inequalities. That is less than epsilon. Let me draw you a picture of what's going on. This will necessarily be a two-dimensional picture, but that's okay. Here is our set Y, our Jordan set Y. We've got a function G and another function F. And then our set X is everything in between here. And now we want to show that X is a Jordan set. That means we want to show that 1 is integrable on X. So we want to come up with a rectangular cover of X. So let me draw this picture again. Here is Y. And then here is our cover of Y. In one dimension, we could make it a partition. We could make it so it only saw points in Y, but in higher dimensions or for weirder sets, we might not be able to do that. And then here is our function G again. Here is our function F. And we build a rectangular cover of Y like this. We take horizontal strips in two dimensions. These would be prisms in higher dimensions, that is, infinitely tall things whose base is a rectangle. And then what we're going to do is we're going to cover it with rectangles that look like this. And that gives us a cover. And let's write out algebraically what that picture is doing. So if I've got a point in X, then Y is in one of the rectangles for some rectangle R in our cover, or P of Y. That's what it means to be a cover. And furthermore, we have that T is between F of Y and G of Y. But F of Y is less than or equal to the supremum over that rectangle of F. The biggest F gets in that rectangle, and G is similarly at least the infimum. over that rectangle of G, or, well, rectangle intersected with Y. I get, as I said, we might have some rectangles that are not subsets of Y. So this set, let's call it S. This is the set of all rectangles where the base is a rectangle in P, and then the height we go from the infimum over the rectangle of G up to the supremum. This is over all rectangles R and P, and such that that's supremum of F is at least as big as the infimum G of G. And I get to do that. I want to do that because I don't want to talk about what do I mean by a rectangle where the top is below the bottom. And I'm allowed to do that because any rectangle where this is not true, we have that. We have that there aren't any points in X above it. What do I want to say about S? I want to say that it is a rectangular cover. Of our set X. And we've just seen that every point in X is in one of these rectangles. I just have to explain why this is why these rectangles are non-overlapping. And that's if we take R prime in P, then R and R prime are non-overlapping. That means their interiors are disjoint. So if I take the rectangles with R and R prime as bases, sort of no matter what the heights are, I take R cross with any interval and R prime crossed with any other interval. Those also do not overlap. If you go back and take a look at the definition of overlapping in video 7.2.1, you'll see that this is the case. Now we are going to need a refinement of S, and this is how that refinement is going to work. On all these rectangles that are contained in Y, we're going to chop off the top bit and the bottom bit. So here, let me write out what exactly is going on. So let's let P1 be the set of all rectangles in R, cover of Y that are contained, that are entirely contained in Y, and also we'll say that the supremum over the rectangle, not over the rectangle intersect Y, just over the rectangle of G, because now the rectangle is contained in Y. That has to be less than the infimum over the rectangle of F. Let's let P2 be all the rectangles that are contained in Y, such that that is not true. and we'll let P3 be the set of all. We'll put it one more requirement. Will require that the infimum of G has to be less than or equal to the supremum of F. And then we'll let P3 be all the rectangles in P so that are not subsets of Y, but where we've still got the infimum of G less than or equal to the supremum of F. And notice that we haven't got all the rectangles in our original cover, but we have got all the rectangles that give where the supremum of F is bigger than the infimum of G. Yeah. And also P1, P2, and P3 are disjoint sets. Every rectangle is in P1 or P2 or P3, but it can't be in more than one of them. Now we are going to build a refinement of F. So let's let Q2 be all the rectangles in F. And Q3 be the rectangles in S where the base is in P2 or P3 respectively. But the rectangles in P1 we're going to have to break up a little bit. So we'll let Q1 be all the rectangles. But now we'll take the supremum of G and the infimum of F. Notice that if you're in a P1 or P2, then your rectangle is contained in Y, and so we don't need to worry about the about taking R intersected with Y. We can just take the infimum and supremum over R. But now notice Q1 doesn't have all of the appropriate rectangles, so we'll take I'm going to call them Q4 and Q5. That are just the leftover bits. Going up to the supremum of F and down to the infimum of G. Then you can check Q is you put all five of these sets of rectangles together. That is a refinement of S. So that means the rectangles in Q1, Q2 are obviously don't overlap the rectangles in Q1, Q4, Q5, and you can check without too much trouble that the rectangles in Q1 don't overlap with the rectangles in Q4 or Q5. Now let's put all this together. The upper sum of f over our partition minus the lower sum of f over our partition plus the upper sum of g over our partition minus the lower sum of g over our partition by assumption that whole thing is less than epsilon. And so now let's figure out what this is. We can write this as greater than or equal to the sum over all the rectangles in P1. So those are a bunch of rectangles contained in our set Y. The volume of the rectangle times the supremum of F minus the infimum of F plus the supremum of G minus the infimum of G. And then we have to add on to this the rectangles in P2. We write the exact same thing. I'm going to write this in a slightly different order. And then we have to add on to that. And then let's add the rectangles in P3. Now we've got rectangles that are not wholly contained in our set Y. So we have to do the annoying thing with the maxima and minima. And this is a less than or equal to because you'll notice I am leaving out all the rectangles that aren't in P1 or P2 or P3. Now let's break this up just a little bit more. So the sum over P1 will break into two pieces. The sum over P2, notice that if you're in P2, then the supremum of G is bigger than the supremum of F. So this quantity in the parentheses is non-negative. So if I decide I don't feel like having that anymore, it's only going to make our sum smaller. And then these two, this thing is non-negative at maximum with 0. Minimum with 0 is non-positive. And then you take the maximum of 0, you get another non-negative thing. So we're going to leave out a bunch of non-negative things. And then whichever is bigger, 0 or supremum of f, that's certainly bigger than the supremum of f minus the infimum of g. I can get rid of our supremum with an maximum and minimum with 0. And now we think about how these sums relate to those rectangles Q. Well, the first sum over, if R is in P1, then R times infimum f up to supremum of f, that's precisely a rectangle in Q4. So I'm going to keep using R for rectangles. And then I'll write times 1. The next one is the sum over all the rectangles in Q5. Then the one after that is the sum over all the rectangles in Q2. Rectangles in Q3. So this, notice, is the sum over all the rectangles in Q minus the sum over all the rectangles in Q1. And so that first piece is the upper sum of the function 1 over our rectangular cover Q. But if R is a rectangle in Q1, then R is contained entirely in X. So the lower sum of 1 over Q, that is at least the sum over the rectangles in Q1, the volume of R times 1. So at the end of the day, we have that epsilon is bigger than the upper sum of 1 over Q minus the lower sum of 1 over Q. And we can do this for any positive epsilon. So by proposition 7.2.4, again, 1 is integrable on X. That is X is a Jordan set. And that is what we were trying to prove. We have an immediate corollary. Which is that all closed balls are Jordan sets. And the proof is a pretty straightforward induction argument. let's define I'll use a superscript n to mean the point a1, a2, up through an. This is the point in Rn, if n is between 1 and p. And let's I'll use a subscript n to emphasize that we're talking about the ball, the set of all points in Rn, such that the distance from y to an is less than r. Okay, now the first one, the ball in one dimension, this is just the interval, the closed interval from a1 minus r to a1 plus r. This ball is a rectangle. It's very strange to say that balls are rectangles, but in one dimension it is true. So this is a Jordan set by an earlier proposition. Then if the n-dimensional ball is Jordan, and is obviously bounded, then the n plus 1 dimensional ball for n less than p, so n plus 1 is no more than p, and therefore an plus 1 is defined. Let's just note that that is the set of all points yt in Rn plus 1, such that y is in the ball in Rn, and also we can write with square roots r squared minus y minus an squared. And that is Jordan by the previous proposition. And because g of y this square root of r squared minus the norm squared, and f of y our upper bound, they are continuous on the n-dimensional ball, and the n-dimensional ball is compact. So we don't need to check uniform continuity or anything like that. We just need to know continuity, and compactness gives us the rest. On your homework, you're going to prove a few things about Jordan sets. You'll prove that a few particular sets are Jordan sets, and the following 3 lemmas might be useful. Now, these are basically things you can do with rectangular covers, where it's sort of easy for me to draw a picture of what's going on and I can write down the useful properties, but we're trying to get into the exact algebraic details, trying to prove rigorously that it works in all dimensions and for all covers gets very, very messy. So I think I will just write down the lemmas. I will draw the picture that gives us the sketch of the proof, and we'll say on the homework and exams, you're allowed to take these lemmas for granted, even if I haven't written the proof out in complete details. So here is the first lemma. Let S be a collection of rectangles in RP. And you might start with a collection of rectangles that don't overlap, but the conclusion is that you can always produce a non-overlapping set of rectangles. Such that I can write this equation. If R is a rectangle in S, then R is the union over all rectangles. I gotta call them something. A and P that are contained in R. And let me draw you, I promised you the picture. So our set S is a set of rectangles that are allowed to overlap with each other. You might even have rectangles inside of other rectangles. It's often going to be useful in the applications for there to be one big rectangle that totally surrounds all the others. And the idea what's going on here is that we're saying if you've got some overlapping rectangles, you can always split them up such that the small pieces don't overlap. Then and any of the rectangles you started with, it's now a union of the rectangles in the new set. So this yellow rectangle, this big rectangle that we started with is the union of these four little yellow rectangles. Here is another lemma. This essentially says that if you start with a rectangular cover, you can make it a little bit bigger. So let's let P be a rectangular cover of some set X. And epsilon be your favorite positive number. And the conclusion is that then there is a rectangular cover S of X with the following three properties. It's a rectangular cover, so the rectangles in S are not overlapping. First off, P is a subcollection of S. Every rectangle P is a rectangle in S. And the rectangles we have added, their total volume is as small as you want. And the final conclusion is that X is in the interior, not just in these rectangles, but in the interior of the union of these rectangles. So let me draw you the picture. Here is our rectangular cover. here is our set X, which it has to be contained in the union of these rectangles, but it is allowed to touch the boundary in various ways. And then the idea is we add a bunch of very small new rectangles. We can add new rectangles that are as small as we want, but they're going to cover all of the bits of the boundary that X reaches. And then I'll point out that in particular, if A is a rectangle, if we need to make our cover S any bigger, so if we throw in any rectangle that does not overlap the rectangles we've already got, then A is not allowed to intersect with X. And here is the third lemma. If we start out with a rectangular cover of X, and epsilon is a positive number, then there is a refinement Q of P and a subset at a sub-collection S of Q, that is a set of some of the rectangles in Q such that we've got the following two things are true. Almost all of the volume is in our set S. The leftovers have volume at most epsilon. And also if R is in S, then R is contained in the interior of A for some rectangle A in our original cover. Let me draw you this picture. We start with our rectangular cover. I'm not even going to draw the set S in this case. And then we slice each of our rectangles into 3 to the P pieces. 1 to intervals, we chop off a little off each end. Rectangles in 2 dimensions, we chop off thin bits near the edges. And then S is these 3 rectangles, these big rectangles in the middle, and notice they're contained in the interior, and the leftover bits, the rest of the rectangles don't have very much total volume.